Hello everyone, welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So in this course Structure Analysis, so far we have completed 11 lectures. The last lecture was Slope Deflection Method. In that we have solved 2 example problems. So in today's lecture, that is a 12th lecture, we are going to discuss about the moment distribution method. So as we know that for analysis of a continuous beam, we have a multiple methods. By using that, we can able to calculate the final end moments. So which is a slope deflection method, moment distribution method, theorem of 3 moment method, and also a flexibility and stiffness matrix method. So in today's lecture, we are going to discuss about the moment distribution method. So the title of the lecture is Introduction to Moment Distribution Method. So at the end of this lecture, students can able to understand the concept of moment distribution method, and also they can able to derive the equation for carryover factor for both the ends are, both the support conditions are fixed and both the support conditions are simply supported. Okay, before that, we'll see what is mean by a moment distribution method. So this method is first introduced by Professor Hardy-Crass in 1930. So that's why the another name for the moment distribution method is Hardy-Crass method. So it is generally used for the analysis of all types of intermediate structures. But the advantage with this method is compared to flexibility matrix method and stiffness matrix method or a slope deflection method, this method is very simpler, and then going to avoid the complex or tedious equations. So in this method, all the members of the structures are first assumed to be fixed in position and then a direction. So we are going to assume the supports are fixed supports, and then we are going to calculate the end moments due to the external loads, and also we are going to discuss the very important parameter, which is the carryover factor. So without the carryover factor, the moment distribution method, we cannot able to solve the problem. So first we need to understand what is mean by carryover factor. So in the lecture 12 and 13, we are going to discuss about the carryover factor. So what is mean by the carryover factor? It is the ratio of moment produced at the joint to the moment applied at the joint. The ratio of moment produced at the joint to the moment applied at the joint. Without displacing it, it is called the carryover factor. Okay, in these 2 cases are there. One is a carryover factor for a fixed beam fixed at one end and then simply supported at the other end. For example, this is the beam, and one support is fixed and the another support is just simply supported. So for this case, we are going to see how to derive the carryover factor for a beam in this lecture. In the next lecture, what we are going to discuss? We are going to discuss the carryover factor for both the ends of the beams are simply supported. Okay, so quickly we can go to the derivation. First, what I am going to discuss? I am going to discuss this one, carryover factor for a beam fixed at one end and simply supported at the other end. So this is for fixed at one end and simply supported at other end. Okay, so quickly I will take the beam fixed, and then here I am taking a simply supported connection. The length of the beam is small letter L. Okay, let's mark the supports. This is support A and then this is support B, and then here I am going to apply the clockwise couple because it is the carryover factor is nothing but the ratio of the moment produced and then ratio of the moment applied. So here the applied moment is mu. The applied moment is mu. Let's write all the notations. L is length of the beam, then mu is applied moment at support B. Okay, applied moment at support B. So this we are applying as a clockwise moment. Okay, we are applying as a clockwise moment. And the notation MA represents moment at support, moment at support A. Moment at support A. Okay, so let's apply these conditions. So we have a fixed beam, fixed at one end, and then simply supported at the other end. Okay, let's assume the reaction force are acting upward direction, and here we have our applied moment. Let's mark it in a different color, which is mu. Okay, so we have the span L. Now, because of this applied moment, how this beam will deflect? The beam is going to deflect like this. The beam is going to deflect like this. So at the support B, let's mark that also. This is A and then this is the B support. You see, at the support B, we are going to have the maximum slope theta. Theta B is maximum value and theta A is 0 because it's a fixed support. Now, here the clockwise couple is acting. In order to counteract that, definitely the MA will be acting in an anti-clockwise direction. Now, I am taking moment at support A, and then I am going to equate the clockwise couple and then anti-clockwise couple. So first look at what is the anti-clockwise couple. So the reaction force R at the B support is acting upward direction and the length is L. So this force R multiplied by L is rotating in a anti-clockwise direction. So this is R multiplied by L. Then what is the clockwise couples here? Definitely MA is acting as a clockwise direction, plus mu is also acting in a clockwise direction. So we are going to keep, this is the equation 1. Okay. Now what I am going to do, in the same beam only, let's take a new page. So in the same beam only, I am going to consider the XX section for a double integration operation. So this is where our reaction force are acting, and here is our moment MA is acting. Okay. So here in support B, the reaction force acting in upward direction, we are considering at support A, R is acting at a downward direction, because here the moment is clockwise in nature. So if it is an anti-clockwise couple acting in at support A, obviously the reaction force will be in upward direction. But in this case, we have the clockwise couple, so we will be having the downward reaction force. Now let's mark it in a different color. We are going to consider the XX section from the support A. We are going to consider XX section from the support A. Now I am going to calculate the moment at that XX section. Okay, the moment at that XX section. In between the support A and this XX section, what are the things are there? Only two components are there. One is the moment at support A and then the reaction force R, which is acting in a downward direction. Okay, so you see the MA is in a clockwise direction, so I put the positive MA, but this load, this reaction force R is acting in a downward direction. that reaction force acting in a downward direction multiplied by the linear distance is x. So minus r multiplied by x. Okay. So this is the equation I got. I am going to substitute this equation in the double integration method. So which is ei into d square y by dx square equal to mx. So ei into d square y by dx square equal to, what is our mx? Our mx is ma minus r multiplied by x. Okay, so we are going to do the double integration operation. Let's integrate it. If you integrate it, then it will become ei multiplied by dy by dx equal to ma, which will be multiplied with x, minus r into x square by 2 plus the integral constant c1, plus the integral constant c1. Once again you integrate it, ei into y equal to ma, then this will become x square by 2. So this will become x square by 2 minus r by 2 into x cube by 3 plus c1x plus c2. So this is the deflection equation. So ma into x square by 2 minus r by 2 x cube by 3 plus c1x c2. Let's simplify this further. So I keep this is ma by 2 multiplied by x square minus of 3 multiplied by 2, 3 multiplied by 2, 6. So r into r by 6 into x cube plus c1x plus c2. So this is a simplified equation. Okay. So this is the equation 1, equation 2, this slope equation, and this is equation 3, which is the deflection equation. So now what I am going to put, so when x is equal to 0, first of all we will take a slope equation. So our slope equation is ei into dy by dx equal to ma into x minus r into x square by 2 plus c1. Now our job is to eliminate this unknown c1, c2. So how to find out the c1, c2 value? We need to apply the boundary condition. So when x is equal to 0, dy by dx is equal to 0. Why? Because this is our x section. When x is equal to, if you put x is equal to 0, then we are at the fixed support. At fixed support, the slope is 0. That's why. Okay. So let's substitute this in above equation. We will put, if you put x is equal to 0, then this dy by dx 0, this will become 0, and this is 0. Wherever x term coming, we are going to simply put 0. So we will be getting c1 equal to 0. Now I am going to take the deflection equation. ei into y equal to ma by 2 x square minus r by 6 into x cube plus c1x plus c2. So already we got the c1 value is 0 here. Okay, so only c2 is left over. So now when we are going to apply the another boundary condition, when x is equal to 0, deflection also 0. For example, any support, the deflection is 0 unless the support settlement is given. So we don't have any support settlement. The deflection at the fixed support is 0. So let's substitute that in the equation. So y is 0, x is 0, here also x 0, then we will be having c2 also 0. C2 equal to 0. So we got the C1 value 0 and C2 value also 0. Now we are going to substitute back the C1, C2 as 0 in the original equations. So now you see the C1, C2 is eliminated. So after eliminating the C1, C2, I am going to have EI into Y, MA by 2, X square minus R by 6, X cube. So hereafter C1 and C2 will be coming, but I am not writing because those terms already become 0. So this is our deflection equation. So in this equation, I am going to put when X is equal to L, deflection is 0. Why? See the diagram. Fixed support, simply support. This is our X section. If you put X is equal to L, we are at the support B. If you put X is equal to L, we are at the support B. There, that location also, the deflection is 0, but slope is not 0. Okay. So, let's substitute that value. So, this is 0, we'll mark it, and then I am going to substitute 0 equal to MA by 2 instead of X, L square minus R by 6 L cube. So we got this. Then we are substituting. Then one more thing we need to consider here. What is that? MA by 2 is there. So MA by 2 is there. We need to substitute what is MA here. Okay, so let's split this into a different form. Go to the equation 1. Here we wrote RL is equal to MA plus mu. Okay, so that we are going to substitute here. So I'll write it here. Instead of MA, I am going to substitute RL. Okay, so we will be getting RL square multiplied by L, and then I am taking a numerator also, denominator I am multiplying with a 3, so I will be getting 6 equal to MA L square by 2. So then this is became R L cube by 6 equal to MA L square by 2. Okay, 0 MA by 2 into L square minus R by 6 into L square, and then after substituting back this we will be getting RL cube by 6 is equal to MA L square by 2. It's very simple, we are just substituting MA is equal to RL. MA is equal to RL we are substituting, or R is equal to also we can able to substitute. Okay, so this is the value we are getting. Now further we are simplifying this, we will be getting RL is equal to 3 times of MA. RL is equal to 3 times of MA. Now we have already this equation, which is R multiplied by L is equal to MA plus mu. So instead of RL, shall we substitute? Already we got RL is equal to 3 times of MA. Let's substitute that value here, 3 times of MA equal to MA plus mu. So what I want this from this equation, I want a mu. So 3 times of MA minus MA. So mu is equal to 2 times of moment at support A. Okay, already we know MA is equal to mu by 2. So mu is nothing but MB by 2. Mu is nothing but the moment at support B. So from this we will be getting MA is equal to MB by 2. So, MA by MB is nothing but 1 by 2, which is 0.5. Okay. So, we got MA by MB ratio. Further, what I am doing? I am taking the equation EI into dy by dx equal to MA multiplied by x minus Rx square by 2. So, this is nothing but the slope equation after substituting C1, C2 values. Here I am going to put x is equal to L for maximum slope. This already we are discussed. So, this is our diagram. So, this is our x section. If you put x is equal to L, we are at support B, and at support B only we are going to have the maximum slope, which is theta B. So, let us substitute in this equation x is equal to L, EI into dy by dx, MA multiplied by L minus R by 2 into L square. So, what we are getting? MA by into L minus, I am going to split this R like this, R by 2 into L multiplied by L. Instead of L square, I am writing L multiply L deliberately, because instead of RL, I am going to substitute the value 3 times of MA. Okay, so because we know already RL is equal to 3 times of MA, where it is? Here it is, RL is equal to 3 times of MA. So, let us substitute that value. So, write it MA multiplied by L minus, instead of RL, 3 times of MA by 2, and then this leftover L. Okay, go to the next page. We will be having 2 times of MAL by 2 minus 3 MAL by 2. So, if you are subtracting this value, we will be getting MAL by 2. So, this is EI into dy by dx. We will say EY into dy by dx is nothing but theta b, because we are calculating theta b only here. So, we will be having, can I substitute MA is equal to mu by 2? So, minus of MA is nothing but mu by 2 multiplied by, we will be having the remaining term L by 2. So, we will be getting EI into theta b equal to minus of mu L by 4. So, theta b is equal to minus of mu L by 4 EI. I want mu. So, mu is equal to 4 EI by L into theta b. So, this is the applied moment. So, we got the value, that is the applied moment. Now, I am going to substitute theta b is equal to 1 for stiffness factor. I am going to apply theta b is equal to 1 for stiffness factor. Then what is the stiffness factor? Stiffness means is the force required to produce unit displacement or moment required to produce unit rotation. So, here what we are having, this is nothing but the moment. 4 EI by L is nothing but the moment. So, if you apply the unit displacement, then what is the moment? In that case, we need to apply theta is equal to 1. So, the stiffness factor also will be getting, stiffness factor is nothing but 4 EI by L. The stiffness factor is 4 EI by L, and also we have calculated, this is the theta b, we have calculated the applied moment and also the stiffness factor by applying theta b is equal to 1. So, this is the carryover factor, and then stiffness factor, and then slope for one end is fixed and other end is free. So in this lecture what we are discussed? We are discussed how to derive. We discussed how to derive the carryover factor for one end is fixed and other end is simply supported. And also we have discussed what is stiffness factor. So this lecture we derived these two parameters. In next lecture we are going to derive the stiffness factor and then carryover factor when both the ends are simply supported. Thank you for watching this lecture. Thank you.